and work. Now this is Unit 1, Lecture 1. That is the first lecture of the first unit of the course. Now, by way of introduction, when we say computer-aided design and computer-aided manufacturing, there are two terminologies which we will try and briefly introduce it here. Now, computer-aided design involves creating computer models defined by geometric parameters. So basically, when you use a software which can help you to create models of design which are basically defined by the parameters in terms of the length, the coordinate dimensions, and then the coordinate points, then with the help of the computer, then you are actually involved in designing with the aid of the computer, which is called computer-aided design. Now, what you basically see on the computer is that you see the models that you have created appearing on the computer as three-dimensional representation of a part, which you can actually visualize it and make some alterations if you can change some relevant parameters and then let the model display respond. Now, what CAD, which is computer-aided design systems, help you to do is that you are able to see objects in a variety of representations. That is, you can rotate them, you can orient them in some directions, and what is important also is that you can actually simulate real-world conditions onto the model. So you can make the model behave like if, for instance, the drawing that you are creating is made up of wood, you can actually assign the wood properties to that model on the computer and let it behave as if it's a real wood, and then it can take that properties and you can subject it to some conditions of the real world and see the response of that wood. So that is in brief what CAD systems or CAD softwares help you to actually do. Now, when it comes to computer-aided manufacturing, which is CAM, basically what you're doing there is using the data from the geometry of the drawing to control an automated machinery. For instance, you can use the drawing dimensions, the coordinates, to actually do what you call a numerical control or computer numerical control, which is a CNC, or direct numerical control system, is a DNC. Now, when we say CNC is basically a form of a machining equipment. It could be a mill or a lathe machine, but it is controlled by an onboard computer. We'll go into details as we go along. So basically, it uses the geometry of the drawing that you've created and use that drawing to control the way the tool will have to move to remove the material from the part if you are to machine the part for real. So you can actually simulate it on the computer, or you can actually do it in an actual CNC machine. So what you notice basically is that since CAD and CAM use computer-based methods for encoding the data, it is possible that these two processes could be highly integrated. That is, you can have a situation where CAD, you just use the computer to create your drawings. You have your drawings printed out and use to do whatever you wish to do with. But you can have a situation where you use a computer to create a model and then use the same computer to then use the model geometry data to actually assign manufacturing instructions to a CNC machine so that it can perform manufacturing material removal to create the part for you. So when you have such situation, then we say that you have an integrated system which is called a CAD-CAM system. Right. Now, in this unit, what we're going to do is you have a brief history of the development of CAD/CAM. We're going to discuss that, and then we look at the features and capabilities of a CAD model. Then we'll come and look at CAM systems and how they influence the overall product lifecycle. Now, after reading this unit, we should be able to do this following. So, the following. These are basically our learning objectives. At least we should be able to write a brief history on the development of the CAD/CAM, which we're going to go through very shortly. We should be able to define what a CAD model is and explain its capabilities. We should also be able to define a CAM system. Right, so we should be able to define a CAM system, and then also we should be able to define a CAM system as well. So just a quick one. So basically, we should be able to define a CAM system and list its features. We should be able to explain the product life cycle and the role of CAD/CAM. Now, we should be able to also list the advantages of a CAD/CAM system. Right. Now, this is the unit content. We have these two sessions. With sessions 1, we should be looking at the brief history in that section. Section 2 is a bit extended. We will look at the definition of computer design. We'll look at the features of CAD models, and we will come to the capability of CAD models, which we will explain subsequently. Then we will look at applications of CAD model in that section as well. Then we come to computer-aided manufacturing. We also look at applications of CAM. Then we will also look at the definition of CAD/CAM tools. Basically, if you want to define CAD or CAM, you can look at it based on what is inside it, or based on implementation of a CAD or CAM system. So we'll go through these basic definitions, and we'll finally look at the typical utilization of CAD/CAM system in an industrial environment. So we'll look at a scenario that, okay, if we are in an industrial environment, how would we make a decision whether or not to go for a particular CAD solution to our basic task ahead? If we have a task on hand and we want to solve that situation, we use a certain flowchart to answer some basic questions, which will make us take some decisions to help us to utilize the CAD in an industrial environment. Now, we will briefly look at CAD/CAM system and automation, looking at the various types of manufacturing systems, and look at the application of computer technology in automation. And then finally, we will look at the advantages and disadvantages as well of CAD/CAM systems. Right. So we come to the brief history of CAD/CAM development. Now, if you look at the CAD/CAM development, you can trace it from 3 main sources, or 3 separate sources. The first source, we say, was an attempt to automate the drafting process. So basically, we used to have drawings being done manually, and so there was that attempt to say, hey, why can't we automate the drafting process and use a computer to assist us in drawing? So these particular developments were pioneered by General Motors Research Lab in the 60s. Now, what they came up with was basically a drafting tool software, how to quickly create drawings using the software. So what they noticed is that there was a great or an important time-saving advantage of that, because if you look at a computer modeling over a traditional method of drafting, you can clearly see a computer model you can quickly correct and manipulate and change some parameters quickly, other than some drafting on the paper. So that was the first important time-saving advantage that was realized when the attempt was made to automate this drafting process from just a manual pencil paper drawing to a computer-based software, using software to create the lines and arcs and the various features. Now, the second source of CAD was in the testing of designs by simulation. So there was that question that, okay, having used a computer to create the models, now why can't we use a computer to then simulate the model and let it behave as if it is a real part, having these parameters as the part? If it is an aluminium, we can give aluminium properties to the part and subject it to whatever load and see the response on the computer. So that is what we mean by simulation. So there was the use of this idea, which is the use of computer modeling to test products, as instead of creating the products and testing it for real and only to find out that it failed. Why don't we create these computer models, test them, and then refine them as and when they fail, and then we can eventually get the right product out without creating products and letting them fail before we test them. I mean, we letting them fail before we redo them. Okay, so you will notice that this was a very important aspect of engineering, which was also pioneered by very high-tech industries like aerospace and semiconductor industries, because they were the high-end industries in terms of technology, and because of the cost, there was a need to really look at a way that cost can be driven down by using a computer to actually do some of these simulations before this is actually translated to the real world of creating the model. So that is the second source. That was in the testing of design by simulation, pioneered by high-tech industries like aerospace and semiconductor industries. Then the third source of the CAD development was the effort to facilitate the flow from design to manufacturing using the numerical control technologies. So the third source was to say, hey, once we created the models, why can't we use the same geometry parameters to then assign a machine tool to actually work and do a material removal or to create the part by using these numerical control technologies. And this actually enjoyed widespread use in many applications during the mid-60s. Now, this actually was a source that resulted in the linkage between CAD and CAM, which is computer-aided design and computer-aided manufacturing. So you could see that there was a trend in the CAD-CAM technologies. Because CAD and CAM was becoming closer and closer, the integration became ever tighter and tighter between design and manufacturing. So you can look at CAD development and look at this linkage between the two, which was very important because it helped to overcome the traditional shortcomings of numerical control technologies. Because basically you could have had your CAD drawing, and then from your CAD drawing you can write your machining instructions and take it to an NC machine. But there was the birth of CNC machines, computer numerical control machines, which means that we can generate the information from the CAD drawing and get the machining instructions from the drawing as well. So that integration was very important to overcome the shortcomings of what NC machines were going to give. So that speed, by enabling design and manufacturing of a part to be undertaken using the same system, was very important, and it actually shortened the period between design and manufacture, and it actually also expanded the scope of production process for which automated machinery could be economically used. So you could notice that just as important, CAD/CAM gave the designer more direct control over the production process, it also created the possibility of completely integrated design manufacturing process. So that is what we can say about this history. Now, you read further, you notice that this technology has grown quite rapidly after the 70s and has made it possible by the development of mass-produced silicon chips, like the microprocessor. Now computers are so cheap, you can easily afford it, and therefore CAD/CAM technology has actually enjoyed widespread growth, because now you can have a computer, you can download the CAD software and then install, and you have a CAD tool that you can use to quickly create models. So as the price of computers continue to go down and the processing power of computers also improving, the use of CAD/CAM has actually broadened from just when it used to be large firms using large-scale mass production techniques to firms of small sizes. You can basically have a desk and you have a CAD tool and you have a 3D printer, which we will come to that in the course of the lecture, and then you can actually have a small manufacturing firm producing some little important engineering products. Now, the scope of operation of this CAD/CAM broaden as well, because apart from just part shaping by the traditional tools such as stamping, drilling, and all that, CAD/CAM has also been used by firms who involved in producing consumer electronics and components, which like molded plastics and a host of other products. You could see that computers are also involved in the use, involved in the control of a number of manufacturing processes, such as if you go to in chemical processing, you see a lot of computers being used in controlling processes, and they may not be strictly defined as CAM because the data is not based on geometric parameters, but computer is greatly involved in controlling some of these manufacturing processes. So basically, when you use CAM, it is possible to simulate in 3 dimensions movement of parts through a production process, and you can actually look at feed rates, angles, speeds of machine tools, and positions of clamps and all that. So as CAD continued to develop, and then a simulation of various processes are also developing, CAD and CAM is becoming integrated increasingly. So you could basically see CAD/CAM system actually also helping communication among those involved in the design. Now, one of these reasons, that is, if you look at the facilitation of communication, is very important, especially in a situation where one firm contracts another firm to either design or produce a component. Once they have the same CAD platform, they could be sharing files, they could be downloading files across and be communicating on the same file. So CAD has been very useful, in its development. So that is a brief history that we talk about for CAD/CAM development. Now let's attempt to define what a CAD is from this section, that is computer-aided design. Originally, if we say CAD, it basically included any technique that used computers in the design process, including the drafting, stress analysis, motion analysis. But for a couple of years now, CAD has been more specific to computer-aided design and drafting. So now when we say CAD, it's basically referring to a CAD program or software. So we say that a CAD program or software is an electronic tool that enables one to make quick and accurate drawings with the use of a computer. Now, the computer systems assist in creating modification and doing some analysis and optimization of the designs. Now, a CAD model, if you want to strictly define it, is basically a visual and a mathematical representation of a part. Now, it can also contain all the design information, including geometry, dimensions, tolerances, material, and manufacturing information. So, a CAD model is not basically the visual alone that you see as a drawing, but within the visual, there is a mathematical representation because, for instance, to create a simple box, you may need the coordinate points for the vertices of the box. Now, the coordinate points may have to have some relationship. So those relationships are representations. Now, these points are joined by lines to create a box. Now, you may have a line either parallel or perpendicular to each other. So these are also mathematical relationships. So these mathematical relationships helps to construct this box, and then we see it as a visual. So we will basically define a CAD model as a visual and mathematical representation of that part. Now, what CAD has, done magnificently is that they've succeeded in replacing the paper blueprints in engineering drawing. Nowadays, you don't see draftsmen holding big sheets of drawing which has been done on a drafting board with a pencil any longer. You will see drawings printed out from a plotter with the aid of a computer-aided design software. Now, if you look at a CAD model, the simplest form of a CAD model is normally what we call the two-dimensional model, which is called a 2D model. Now, when we say a 2D model, it's essentially the computer graphics equivalent to an orthographic projection. So for those who have done a little engineering drawing, once you have a drawing which is in an orthographic projection, that is where you have elevation, the plan view, and view, then that is a two-dimensional model, and that is the simplest form of CAD model you can have. Now, the CAD model, which after the two-dimensional model, the upgrade of a CAD model is a 3D model, which is a solid model, which we normally call the 3D model. It is the most general form of CAD model used in the CAD software, and it is also an equivalent of an isometric view that you see on the drawing. So when you take this 3D model, also we have two basic types of the 3D models, and that is we have the wireframe and the surface model. These will be explained further. The wireframe is basically a model where you can only see the edges of the objects. So when we draw an object and all you can see is a bunch of lines forming the edges, then we say this representation of this model is in wireframe. Now, a surface model is the model that defines the object in terms of the surface, such as plates and shells that are actually enveloping surface. So when you have a box, and basically you can color the faces and see all the faces wrap up together to give you an impression of the box. Then we say, if you look at it from the surface, it's actually a surface model. Now, if you have a box which is just showing an outline with the edges alone, then you have a representation of that box in a wireframe model, right? Now, when it comes to CAD models, you can basically talk about features of the CAD model. Now, a CAD drawing has the following characteristics. A CAD drawing is neat, clean, and highly presentable. You can modify a CAD model easily. Now, when you have CAD drawings, you can have the parts modeled, visualized, and revised, and also improve the model on the computer before any engineering drawing is created. Now, parts that has also been modeled can also be assembled in a virtual environment, so you can see the assembly on the computer screen, and you can even turn around to see all other views that you may not see when it is on paper. Now, you can also simulate relative motion between the parts. You can actually do animation to see it on the computer. You can also analyze computationally and redesign the part if necessary. So you can also use the CAD model to do machine tool power for mold filling flow to actually fabricate the part. You can do that all on the computer. Now, the part can then also be downloaded to a rapid prototyping system. This is a system we shall discuss later, but it's basically from your computer to a rapid prototyping system, and then that is a rapid prototyping machine, and that machine will create the physical model in 3 dimensions in a few hours with virtually little or no human intervention. So from your computer drawing, you can get your solid part in a couple of hours using the virtual, the rapid prototyping system. Now, we can look at the capabilities of CAD models in this representation that has been displayed in boxes. So when we take capabilities of CAD models, we can look at it from presentation, flexibility in editing, unit and accuracy level. We can look at storage and access of drawings, sharing of the CAD drawings, project reporting, engineering analysis, and computer-aided manufacturing. So these highlights the capabilities. We're going to pick them one by one and briefly explain. Presentations. You can use a CAD model to create fine drawings with presentation symbols and textiles. That is, you can create PowerPoint presentations using your CAD model. And then you can actually use the CAD program to make screen presentations. Now, flexibility in editing is quite obvious. When you have a CAD drawing, it provides you the flexibility to make these quick alterations of the drawing. Some of the editing capabilities, such as move, copy, drawing elements, enlarge or reduce and make multiple copies of all that, change units of measure. You can do this very easy, and it's quite flexible in the software. Units and accuracy level, fantastic. The CAD program will allow you to work with great accuracy, because once you click a line and you dimension as 10 centimeters, it is exactly 10 centimeters from the computer. Now, you can also work with different units of measurement, such as you can even work with architectural units and engineering units, scientific units, and surveyor units as well in the CAD model. Storage and access of drawings. Now, it is also a very quick and convenient way to organize CAD drawings. Now, you can have thousands of drawings on a hard disk or in a drive, and then you can open any one of them within seconds. Now, unlike paper drawings where you have to carry a bunch of drawings together and then sift through to actually look for the drawing that you are interested in. So, storage and access has great capability there. Now, sharing CAD drawings. The drawings, you can actually share it with a number of users, allowing them to coordinate the projects and work as a team. You can have one single file being worked on by different people connected to different computers through a network, and they will be working on the same file and making changes and saving them. And then you can also publish your drawings on the internet for collaboration or for collaborating design, because you can get people on the other side of the globe look at the drawing and then make inputs and all that. So sharing of CAD drawings is very important. You can also use CAD for project reporting. Now, the CAD software can be used to prepare project reports. You have engineering analysis also that you can use the CAD software to do. You can actually have a separate or an integrated program in the CAD software. That is, you can have a computer-aided engineering software which is integrated with the CAD drawing software for engineering analysis. Then also you can have a computer-aided manufacturing. So you can have CAM as a method used by large corporations to do manufacturing. That's computer-aided manufacturing. But to use the CAM, you need the CAD. So the systems will import CAD drawings into the CAM programs to automate the manufacturing process. So CAD software programs or CAD drawings will help automate manufacturing process that will greatly assist in CAM. Now, when it comes to applications of the CAD models, we've seen the capabilities. Applications of CAD models, you can actually use CAD models for stress analysis, heat transfer analysis, free flow, and then you can also use it in CAM and in a general context in computer-aided engineering. Now, in the manufacturing process, you can also use the CAD model to automatically generate machine tool path for the machine, for machining an object. That is, if you want to use a CNC machine, you can use your drawing to generate the CNC codes for the manufacturing to proceed. Now, you can also use the CAD to simulate the removal of the material from an initial block of the material on the computer, so that you can see that whether you are going to achieve the actual final shape of the part. By doing this simulation on the computer, that will help you to know the final shape. Now, you can also link this CAD model to a computer numerical control machine, now a CNC machine, to carry out this material removal automatically, allowing a lot of identical parts to be created. Because once you create a CNC program to machine that part, you can repeat that program, run it over and over. So if you have to create a multiple of these products, you can use the same program to run it several times and create those parts. Now, you can also use the CAD model to build assembly models of products by defining the mating relationships between them. So you can basically bring onto a screen a number of CAD parts and then put them together in assembly virtually to actually build an assembly model, so that you can visualize the parts that are together in one file and in one view. Now, you can also use CAD to evaluate designs and do a redesign. So we have a whole technical design for assembly and design for disassembly as well. So you can use the CAD model to evaluate the design, and if there is a need for redesign, you can actually do that as necessary. You can also use CAD for arriving at what we call optimum designs whenever there are alternative or feasible designs. So you could have various types of optimizations that you can actually do. We have parameter optimization, we have shape and size optimization as well. So you can basically use CAD to do a number of these. Now you can also use CAD for what you call virtual prototyping. That is, you can just use your CAD drawing to create, physical prototype. You just do a virtual prototyping environment. You create a CAD model environment and you simulate the behavior of the component. So you have the drawing on the screen and the drawing is behaving as if it is a real component. Then you put the system conditions of that part to the drawing, and so you assign the drawing the material properties, and then you will see how the drawing will behave on the screen. So now the drawing is representing the model. So you actually simulate the behavior of the component or product under this environment using what we call the laws of nature. Of course, you use the laws of physics. Now, you can also use CAD to assist in collaborative design. Of course, we can have a number of designers geographically distributed over the globe, and then they'll be participating, working on one single file. So one will take the particular file, make some changes, save it, and then update it on a network, and then others will carry on with the same file, and then eventually they will create the final part. Now, when it comes to computer-aided manufacturing, we should talk about computer-aided design. So now let's look at computer-aided manufacturing. Computer-aided manufacturing, basically using computers to assist in manufacturing process. Now, basically, if you look at CAM, you can apply it to all types of manufacturing scenarios. So what CAM is that if you want to define CAM in a brief sense, you will say that it involves the use of a computer systems to plan, manage, and then control. So you basically doing these operations. So you plan, you manage, and then you control the operations of the manufacturing plant through either direct or indirect computer interface with the plant's production resources. So from the definition, you can see CAM falls into two broad categories. So the first is computer monitoring and then control. And then you have manufacturing support application. Now, basically you are using the computer to control a process. Now, to control a process, of course, you will need to control a process data. And with the help of control signals, you are able to control the process. Now, when it comes to manufacturing support applications, it's the same computer that you are using to control manufacturing operations, and also involves some data that you're processing, and then that is also being registered by some control signals. So that is computer-aided manufacturing to two broad categories: computer monitoring and control, and then computer support application. Now, when it comes to examples of computer-aided manufacturing, we take a number of them. Now, the first is to look at design for manufacture, or design for manufacturing, DFM. Now, this is an example of a computer-aided manufacturing philosophy where any aspect of the design process in which the issues involved in manufacturing the object are considered with a view of influencing the design. So you are designing, but you are looking at the manufacturability aspect of the design for you to make an informed choice in the design decision That is, based on the difficulty or challenges you may have in manufacturing, the design could change. So the designer will make use of a computer-aided manufacturability analysis tool to get a feedback about the ease of manufacturing, suggestions for redesigning the part. So in such a system, typically what you have is that you have what we call manufacturability advisors being used to analyze the design for ease of manufacture and from various manufacturing process viewpoints. So if you take this typical flow chart, that is, if you have your design model would be sent through a manufacturability advisor, which is a tool. Now this manufacturability advisor will utilize a knowledge base, now which is more like a database of manufacturing capabilities. Then it will perform a manufacturability assessment on the part. Now the result of this assessment normally comes in two folds that we're going to look at here. The result of these two is either a manufacturing advice or a redesign suggestion. So it's either your advice about particular features that you will need to check to ensure that your design passes the manufacturability assessment test, or a suggestion for redesigning the part will also be output, so that you can consider perhaps changing the whole design of the part. Now, another example of computer-aided manufacturing is what we call computer-aided process planning, CAP. Now, in computer-aided process planning, it basically refers to complete planning of the manufacturing process. That is including raw material selection, machine selection, process selection, setup planning, process sequencing, and manufacturing time estimation. So all the aspects, complete planning of the manufacturing process, you can involve computer-aided manufacturing tools. So if you look at a CAP, which is computer-aided process planning, we say that it refers to a partial or complete automation of the process planning activities. So you can have a computer-aided process planning, which is a complete automation of the process planning. Now, what happens in computer-aided process planning is that you have a process planner that makes a detailed plan on how to go about manufacturing a product or component with a greater assistance from the computer. Now, though you haven't really achieved complete automation, what you will notice is that industries are moving closer to this kind of computer-aided process planning solutions. But yet, we haven't gotten to complete automation really. Now, the third example of computer-aided manufacturing is the utilization of what we call computer-based predictive models. Now, when it comes to predictive models, they basically use the laws of physics to understand manufacturing or manufacturing phenomena and help them arrive at efficient process plans. Now, examples are as follows. For instance, we have a computer-based predictive model which is called two-way prediction in machining. It's basically helping you to know the time required to change a tool insert. So if you can simulate to actually know the time required to change the tool insert, then it greatly assists in the process planning, the manufacturing process planning. Then you can have a predictive model for estimation of solidification time in a casting process. So you can have a predictive model that can tell you how long a particular casting will solidify, which is very important. And also we have what we call a spring back prediction in sheet metal forming. This is a common problem actually. In sheet metal forming, by stamping, once you create the process and you stamp out the shape of the part, there is what we call a spring back effect. That is the part springs back a little, and so the original shape that you created was sprung back, which means that's reduced in size. Now you should be able to predict this successfully when you are doing sheet metal forming, because that can be a very serious problem when it comes to die design. Because if you are using the metal forming to create a die, and the die has sprung back, it means it has reduced the size of the part. If you don't predict it, then you may turn out an undersized part. You can also use these predictive models to do a prediction of the heat affected zones in a welding process. Okay, so we move on to the fourth example of computer-aided manufacturing. And the fourth example talks about virtual manufacturing. Now, in virtual manufacturing, as I've explained previously, is basically using computer models and manufacturing-based simulations to evaluate many production scenarios to optimize the design of the product or the process. Okay, virtual manufacturing is, becoming very useful because, the evaluation of production scenarios in the real world is becoming very expensive and time consuming. So if you are able to do it virtually, you save time and then you save some money. For instance, you can do virtual machining. That is just do virtual material removal. Now this virtual machining can help you identify problems such as two-motion collision so that you can correct the program. You can actually do mold filling simulation to actually know the regions where the molten material could not reach, so the part or the component will have to be redesigned. You can actually do a virtual die design for the casting. Then you can actually do a virtual assembly line design as well. Okay. Now, the fifth example is computer-aided assembly planning. Now, what you basically see is that computers are used to plan optimum assembly sequence to reduce assembly times and costs. Now, you can also use computers for power planning of robots for assembling process, and also efficient planning of the power of robots. Because in assembly planning, you basically have to simulate robotic movements. It is necessary to ensure that these robots do not jam into the parts during the assembly process, because the robot is not a human being. It can basically do what it has been instructed. So if you don't simulate the power of the robot's movement, it may end up jamming into the parts that it is supposed to assemble. Okay. So now the sixth example of computer-aided manufacturing is what we call computer-aided inspection. Now, in computer-aided inspection, you can have what we call computer-controlled inspection equipment, which is a CMM, coordinate measuring machine, profile predictor. So you can have a system where you have a probe which is measuring the profile of the part and then checking it against the standard size and then passing it or failing it as the case may be. That is doing a quality control of an inspection. Now, you can also have a computer-aided inspection setup planning. which is very important because it's one of the important decisions in inspection is really how to set up the inspection process. So if you get a computer-aided inspection setup planning, that really helps. Then you have computational metrology. That is measuring the flatness of a part. So you can have computer-aided inspection technique that will probe to check the flatness of the part. Then you can have a computer-aided part localization to compare two geometries. Both has to be localized in the system. So you may have one geometry localized with some coordinates, and then the other one will be superimposed to check whether or not this is fitting the geometry so that it could be accepted or rejected as the case may be. And then 7, you have computer controlled machines and equipment. Now in manufacturing, you have computers being used to replace the manual effort. And also acting as an interface between the human being and the machine, which really facilitates manufacturing process. So you have CNC machines being computer controlled machines, you have coordinate measuring machines, you have robots, you have rapid prototyping machines, and then these are just few examples that you can have as computer controlled machines. Okay, so now let's look at a typical product life cycle, and look at how CAD can sit. Right. Now, if you take a typical product life cycle, we have the design process, and then we have the manufacturing process. Okay. Now, in the design process, a design process basically starts with a design need. It basically starts with a design need. Okay, then you have the definition, specification, and requirements. Then you collect relevant design information and do a feasibility study. Now, in this process, you will be synthesizing the information. So this side is called synthesis, information synthesis. Collecting the design information and then using that information to also do your conceptualization is all part of the synthesis. From the concepts, you come out with a design model. So you create the model and then do a simulation. After simulating the model and realizing the model is okay, then you may need to perform design analysis and optimization, evaluation as well. And once your evaluation is complete, you have a design, and then you have documentation and communication that has to be sent to the manufacturing process. The manufacturing process will begin with a process planning situation or process planning activity, where production planning will take place, design and procurement of new tools, other materials. You do NC and CNC, DNC programming if required, before you move on to production. And in all these cases, you are in the manufacturing process. You move into production, and then there will be quality control measures, packaging, and then shipping, then to the market, and after market, the information from market feeds back to the design, and the process continues as a cycle. So you notice that this product life cycle has a first part, which is the design process, and then the next part, which is the manufacturing process. So in the design process, you have the analysis, synthesis, and analysis going on, and all involve CAD process, the use of computer-aided design software. And then in the manufacturing process, that is the use of the CAM process. So you have design process and the manufacturing process in the product life cycle. So the product goes through two main processes, design and manufacturing. Now in each of these processes, in the design, as we said, we have synthesis and analysis going on. And then in the manufacturing process, it will begin with process planning, and then, which is the backbone of the manufacturing. The outcome of it will be a production plan, to procurement, material ordering, and machine programming. And then production continues and then the quality control, packaging, shipping, and back to the market. Okay, so let's basically look at the implementation of this CAD process on a CAD/CAM system. Now, if you look at the CAD/CAM process, we've looked at that, and then a typical design product life cycle. Okay, so the next part that we are going to look at is implementation of a typical CAD process on a CAD/CAM system. So we're just going to look at, if you take a CAD process, what is involved in a CAD process? And then what do we finally get from a CAD process, which is then fed to a CAM process? So if you take any CAD software, when you have the geometric model, within that geometric model, if you take the software, within the software, the geometric model is what we see as a representation on the computer screen. But within the software, there is a translator which will actually delineate the model for, within the computer, because we see a drawing, but the computer will see a bunch of logic, program that is being executed. So the translator will then translate that to a geometric model for us to see. Then, of course, if we want to perform some analysis, there will be need for some algorithms, which we normally call interface algorithms, to do design and analysis. Then after we've done the analysis, then we go to do the drafting and detailing. Okay. So then after drafting and detailing from the design, then we produce the documentation. It's from the documentation that now we are ready to go to the CAM system, that is to the CAM process. So you have now your drawing, your documentation and everything, and then you are ready for the CAM process. Right. Now, we notice from this flowchart that if you have CAD 2, there are, in each phase of the design process, there are certain tools that you require to support, the CAD tools that require to support the design process. If you take the design phase, in the design conceptualization phase, basically what we're doing is we're creating geometric models. So that technique is what you require. And the CAD tools that you use basically involve graphic aids, manipulation, and visualization. Now, when it comes to design, modeling, and simulation, it's the same situation that you have. That is, you have the need for some geometric model, but in the simulation, you combine animation, assemblies, and some packages. Then, when you are doing a design analysis, you need certain analysis packages and customized programs and packages to do your analysis, depending on the type of analysis anyway. And then when it comes to optimization, you need customized applications to actually do some structural optimization. Design evaluation, you need dimensioning, tolerances, bill of materials, and then you may need some NC program. And for design communication and documentation, you'll be doing detailing, drafting processes. Okay. So that is typical CAD and the tools that are required. Now let's look at a typical CAM process. Now when we take a typical CAM process, you have a geometric model, and then you have an interface algorithm, process planning, and then NC program, an inspection, assembly, packaging, etc. Then you go to shipping and then marketing. Okay. Now, when it comes to CAM tools and the required supporting manufacturing process, this is a CAM process. Now, it means you're coming from, to get to the CAM process, you should have your geometric model, and then of course there will be some interface algorithms that will be used to actually create a process planning. Then you may have some NC programs, numerical control programs, to actually machine your part, and then you may go to inspection, assembly, and packaging to ship it. Now, in this CAM process, there are some tools that are required to support the process. In the manufacturing phase, when you have process planning, in process planning, we have computer-aided process planning techniques. That is, in fact, you can have cost analysis, material and tooling specifications in there. Then you come to part programming. You will probably need an NC program. Inspection, you can use a computer-aided quality and inspection software. In assembly, you can use robotics in simulating and programming the assembly process. So these are tools that you may require in the various supporting the manufacturing processes one way or the other. Okay, so now you come to the definition of CAD/CAM tools. Now, when it comes to CAD tools, first we are going to look at the definition of a CAD tool. When we say a CAD, the CAD tool can vary from a geometric model, such as just the graphics that you see, and then an interference checking on the extreme, to just some customized or application programs such as just doing some analysis or optimization. So the question is, if you take a typical CAD software or CAD tool, what do you see as the constituent? What constitutes a CAD tool? Now, for a CAD tool, you will basically see a CAD software made up of some design tools, and then you will have to have heavily supported by what we call a computer graphic concept. So you have a CAD tool, and let's say you have your computer which has the capability of displaying the graphics, and then you can use that tools to create a geometric modeling. So CAD tools are made up of these three: design tools, computer graphic concepts, and the geometric modeling. Now, if you define this further on to look at, okay, how do I get a CAD tool? That is looking at the definition based on implementation. To get a CAD tool, you basically need some design tools or the software program and the computer. So what is happening is that the computer has or brings the hardware side of it, the control unit, display terminals, and of course the input and output devices. And then you have the software coming from the design tool, which is the software, graphics modeling, and some applications. So if you have a design software and a computer, then you have what you call a CAD tool. Alright. Now, if you look at CAM, computer-aided manufacturing, the same way for a computer-aided manufacturing tool, you basically need CAD as a CAD drawing or a CAD model. And then you need manufacturing tools. And most importantly, you need a network concept or a network capability so that you can actually link the CAD drawing and the manufacturing tools. So with the help of network concepts, you have manufacturing tools, and then you have a CAD and the network concept, you create that CAM tool. Okay, so in the same way, if you want to look at CAM tool based on how to implement the CAM tool, then the question is, how do I get a CAM tool? I want a computer-aided manufacturing tool. You need a manufacturing tool that's a software, CAM software, plus a computer. So for the computer, you have the hardware as usual, the control unit and all the terminals, display terminals. Then the manufacturing tool, of course, will be the software. The software should be able to import a CAD model, and then the software could be an NC, a manufacturing resource planning software, MRP or something. That will help you to get your manufacturing tools and the network concept. So with this, the software, network concept, and hardware, which is the computer, you'll get a CAM tool. Okay, so we basically say that the main factors that determine the success of a CAM or computer-aided manufacturing implementation are these three. That is, for a CAM system, the link between CAD and CAM must be two-way route. The reason is that if I have a software or a CAD software, I have a CAM software that is able to import a CAD software, there should be a chance for me to edit the CAD software, a CAD model, and then send it back to the CAM software, and vice versa. So that we say that the link between the CAD and CAM must be two-way route, so that I can make changes in the CAD model, send it back to CAM, the manufacturing system, simulate the manufacturing. When I notice there are problems, I send the CAD back to the software, the CAD model to the CAD software, and make changes. So we say that the link of the CAD and the CAM must be two-way route. Now the hardware, the software, and the networking of the various CAM elements has to be in place. So of course, if you need the CAM software, you have so if you need a CAD software, you have your CAD software, you have a computer. Of course, you have a CAM software, you have your manufacturing tools, and with the same computer, but you need the networking of the various CAM elements. So the hardware should be there with the computer, the software will be the CAD software, and then the CAM softwares, and then the networking capability of the various CAM elements. And to link CAD-CAM system, especially when we're dealing with other systems like robots and vision systems, then we say that timely synchronization among these robots and vision systems and manufacturing cells and material handling systems and other shop floor tasks are so important. The reason is, if you have a CAD-CAM system and you are basically dealing with robots and other vision systems, they have to be timely synchronized, because every robot or vision system should know what the other is doing, because there is a possibility of fatal accident, jamming into, and completely destroying parts. Synchronization is very important, so that when there is a problem in a particular system and it stops, all the others must be signaled to stop, so that there will be no confusion. So, if we take a CAD CAM and we put them together and we want to define it, we looked at CAD separately, we look at CAM separately. But when we put them together and say, call it CAD CAM, then if you want to define the CAD CAM based on what you see, the constituent. So if you have a software or a tool that we call a CAD CAM system, then basically that CAD CAM system or CAD CAM tool should have a computer that has the ability to give you a graphic concept display. You should have a manufacturing tool, you should have a design tool, and then of course that design tool should be able to create a geometric modeling, and overall there should be a network integration and automation capability so that you can have a CAD CAM tool. Now, when you have a CAD CAM tool and you want to define it based on implementation, that is, if I want to get a CAD CAM tool, what do I need to get a CAD CAM tool? Basically, you need a design manufacturing tool plus a computer. That is, you need a hardware, you need a software, and you need a networking capability. So, you have hardware which comes from a computer, you need a software which is the software, the design software, the manufacturing software. And then the computer also should have a networking capability. By this you have your CAD CAM tool. Right. So now we have a CAD, we have a CAM tool, and now we have seen a CAD CAM tool. Okay, so the question is, if we have to utilize any of these CAD CAM systems in an industrial environment, how do we go about it? I'm going to give a scenario and use that scenario to explain this flowchart. Let's say we are in an industry where we are using a particular CAD software or CAM software. Does it mean we have to go for, if we have a task to perform, do we have to go for the latest CAD software or CAM software, discard what we are using previously, and then implement that? That is the question. And the answer will flow from this flowchart. The answer is not necessarily yes, that you should go and discard what we are using and go in for a new software. The philosophy is that if it hasn't broken, you don't fix it. So let's look at a typical scenario. For instance, if we have to create a task, we have a design task, and we have a system software in an industrial environment, we use that to create the geometric model concept. So we create a conceptual design. Then we have to ask this question. Now, from our software, can we do design evaluation with the standard software that we have available? If the answer is yes, we'll go ahead and do the design evaluation and testing. Now, if our final design is applicable, we'll go ahead and produce our drafting, that is part drawings, and make the documentation, and we are ready to manufacturing, where we will take it to process planning, and with the use of some CAP packages, that's computer-aided process planning packages, they check whether in this particular drawing or model there are no manufacturing discrepancies in the CAD database. So to go back, if there are discrepancies, then they will go back and check the model. And then the cycle repeats. But if there are no discrepancies, then straight away we look at our NC programming by the help of some of the NC packages, go into machining, inspection, assembly, and then we are ready to package the product. However, if we create the design, the conceptual design, and we notice that design evaluation is not possible with the standard software, that is, if it is no, then instead of throwing away the whole software that we have, we can actually develop a customized package for that task alone, or we can go for a customized package. Okay, so once we use a customized package to help in the process, then we can go back and continue, and it means the evaluation is now possible. Then we do design testing, evaluation, and all the way through. So what we're saying is that in a typical industrial environment, how you utilize the CAD/CAM system is that you don't chip away everything or throw away what you have currently available, but what you do is you look at whether or not the current system of software packages can adequately address your challenge. If not, you go for customized programs. You don't necessarily chop and change everything that you have been using previously. Okay. Right. So we move on to the next side of this introduction, which we're going to look at automation and CAD/CAM. Now, when we say automation, we can basically define automation as the technology concerned with application of complex mechanical, electronic, and computer-based systems in the operation and control of the manufacturing system. Now, we have types of manufacturing systems. One, we have the continuous flow process. Two, we have mass production of discrete products. We have that is mass production of discrete products. 2, 3, we have batch production. And then 4, we have job shop production. Now let's quickly explain these 4 types of manufacturing systems. For a continuous flow process, you have basically continuous dedication of production of a large amount of material. And for instance, you can take a lot of food industries like beverage industries, Coca-Cola, malts, and all that. They produce this continuous flow process, basically filling a bunch of bottles, and they are dedicated in production of large amount of bulk product. Now, in mass production of discrete products, you could see that here there's a dedication to production of large quantities of one product, perhaps with some limited model variation. These are typical examples of automobiles. When we take automobile, that is cars, you have what goes on in car production as mass production of discrete products, because the car as a product is made up of a number of components. So it's not just one product, one bulk material. So they have a number of products, parts joined together to form the car, and then we have it being produced in a mass scale. Then we have what we call batch production. Now the batch production is limited to medium lot sizes, not on a massive scale, but of the same product. So it could be, for instance, if you take maybe books, particular batch of books, the same clothing and certain industrial machines. You can have tractors of a particular model. You can have some machine equipment of particular models which have some serial numbers that depicts that they belong to a particular line batch of production. Right. Then we have what we call the job shop production. The job shop production is production of low quantities, often one of a kind, maybe a specialized product. For instance, normally comes with the aircraft and some other machine tools and equipment. We can have aircraft that is one of a kind. You take the U.S. President's aircraft, which is called the Air Force One, is only one of a kind, and there is no other aircrafts like the Air Force One. So that can be considered as a batch, a job shop production. It's just one particular product. Okay, they have several what they call aircraft carriers, which is like a big ship on the sea, where they use for wars and other things, where the aircrafts, the jet fighters will land and take off from it. Those ships or aircraft carriers, they are one of a kind, and they have special names for it. For instance, the US has the USS Cole, USS Abraham Lincoln, and all that. They are just ships, big ships, which are very big landing platform for aircraft to take off and land. So these are created one of a kind, customized for particular application, and they are technologically complex, and they are done during job shop production. Now, when it comes to these four main manufacturing processes, take continuous flow, mass production, batch production, and job shop production. You have production quantity against product variety. What you notice is that if you take a continuous flow production, the production quantity is quite high, but the product variety is very low. It could be just one single product. Now, when it comes to mass production, in mass production, the production quantity is not as high as continuous flow production. However, the product variety could be, it could vary from just one model to a number of models. Now, when it comes to batch production, the production quantity may not be as high as mass production, but the product variety could be of several batches. And then you come to job shop production, the production quantity may not be as high as batch production, but the variety could be as numerous as possible. So you could see a trend from continuous flow to job shop production. The production quantity actually decreases as you go down, but the product variety also changes alongside. Right. Okay, so now, when you look at these categories of manufacturing, continuous flow, mass production, and batch production, and also job shop production, you can actually look at them and look at the degree of automation, that is the automation achievement in these categories of manufacturing. When you take continuous flow processes, you have flow processes from beginning to end, and that is if you take like beverage production, like Coca-Cola, malt, and all that. In those places, you could see that sensors technologies are very available to measure important process variables. They also use quite sophisticated control and optimization strategies, because they can look at the quantity of maybe the coke, the volume of the coke that they have in their reservoir, and then slow down the process of bottling such that they will just sustain the production. And so there are several optimization strategies that they can use. Now, you can actually have a fully automated line, which is not attended at all, just a bunch of sensors that are controlling processes. Then you have mass production of discrete products. Now, in mass production of discrete products, what you have is automated transfer machines. You could have dial indexing machines, and it ranges from partially to fully automated assembly lines. You take a car model, for instance, each of the model may be on a different assembly line, and then with the use of industrial robots, they be used in spot welding of the parts, and then parts handling, machine loading, and then even in spray painting, there's a use of robots in doing this work. And you could have automated material handling systems, and then computer production monitoring going on. So these are some automation achievements you can have there in mass production of discrete products. Now, in batch production, you could have numerical control, direct and computer numerical control going on. We shall deal with this CNC and DNCs later. And then we have adaptive control machining, robots for arc welding, parts handling, and you could have what we call a computer integrated manufacturing system, which we will talk about it as a whole unit subsequently. Now, in job shop production, you can also have numerical control, that is computer numerical control being used. So these are some automation achievements you can have in the various category of manufacturing processes. So if you look at these things that we have observed, now let's look at applying the computer in the automation here. Now, what you notice is that most of the automated production systems implemented today make use of computers. And if you take CAD/CAM, we are looking at automation and then the role of CAD and then CAM, that's computer-aided design and manufacturing. Now, CAD/CAM also make particular emphasis on the use of computer. Now, it is distinguished by the fact that it includes not only manufacturing operations, but also design and planning functions. So CAD/CAM is not only looking at manufacturing, but design and planning functions. So let's look at the differences in the scope between automation and CAD/CAM by looking at this mathematical model here. Now, if we use this model to represent the total time during the product life cycle, this is TTLC, given by this mathematical expression BQ T1 plus B T2 plus T3. Now, B refers to the number of batches produced throughout the product life cycle of the particular product. Q is the quantity, the number of units produced in each batch. Now, T1 is the time required to produce 1 unit of the batch. So if you multiply these three, you are now going to get a total number produced. Okay. Now, the second part of this equation has T2. T2 is the time associated with setting up for each batch. So B times T2 will give you the time associated for setting up for all the batches. And then T3 is actually the time required for designing the product and for all other activities that are accomplished once for each different product. So T3 is for design. T2 is for setup planning, which is more of manufacturing. T1 is the time to produce 1 batch. Okay, so let's see how automation plays a role, and then the role of CAD/CAM and then automation here. Now, if we try to simplify the the equation and look at the average time spent on each unit of the product by dividing it by the batch and the quantity. These are how the equation turns out. Now, T1 is the time required to produce 1 unit of the batch. So you notice that T1 is the most important term when it comes to mass production and batch production, because you would want to know how long it would take you for one product to be produced. Okay, now T2 and T3. T2 is time for setting up. So it becomes very important for job shop manufacturing, because setup time in a job shop manufacturing can be very high. And then T3, the time for designing. And then for a job shop production, it is also very important because sometimes for just a single product you are producing in a job shop, the design time can take a very long time, spanning from a couple of months to a number of years. Okay, for mass production, the designs are very simple, so this T3 is not so critical. Okay, so if you look at automation, automation will be concerned at looking at these two times, T1 and T2. Automation will help you to produce one batch quicker, T1, and also if you involve automation, the setup time can be shortened. Okay. However, if you look at CAD/CAM system, it is concerned in reducing all these three, but perhaps you notice that T1 could be exclusive for automation, but T2 and T3, which is set up by using CAM systems, and T3 design by using CAD, powerful CAD software, you can actually reduce T2 and T3. So you notice that in a total product life cycle, automation actually is more looking at T1 and T2, and then CAD/CAM is actually also looking at T2 and T3 in terms of the total life cycle. Right. So this is what we wanted to show up here. Okay. So let's talk briefly on advantages of CAD/CAM systems to end the unit. Now, if you look at modeling with CAD systems, they offer a number of advantages over traditional methods that use rules, squares, and compasses, which we have gone through a lot of them. For instance, you can have designs that can be altered without erasing and redrawing. You can have CAD systems that also offer zoom features that are just analogous to lenses of the camera. So some of these are the advantages that you can enlist, apart from the ones you have already considered: flexibility, reduced lead times and inventories, productivity increment, improved customer service, product quality, communication, supplies, and all that. The list goes on to look at greater manufacturing control, supporting integration, reduced cost, increased utilization, and reduction of machine tools, and less floor space. So all these things are basically part of that. Okay, so to actually end the course, by way of self-assessment, should be able to explain some of the capabilities of CAD, list 4 features of the CAD. You should be able to also define CAD tools based on their constraints, and define the tools based on the CAM tools as well. And you should be able to also explain some advantages of CAD/CAM systems. Right. Now, this is a very important assignment, which is normally given at the end of the unit, and that is assignment 1, unit assignment 1. You are to write a report, maximum 10 pages, on the development of CAD/CAM industry from 2000 to date. And your task is that you discuss the performance of the following CAD softwares currently on the market. You have AutoCAD software, SolidWorks, CATIA, Autodesk, Siemens, PLM, Pro Engineer, Solid Edge. In fact, you can add a number of them as well that you know on the market. But you're writing a report to look at each of these softwares, how they have developed from 2000 to date. Okay, when they started, or what was the software, what was the capability, and what are the other software they have developed under their portfolio, and what they are capable of doing now. So that is what you are trying to report on. And this report should have a body. Of course, it should have an abstract, a body, a conclusion, a reference. Okay, and it has to be a proper report. Okay, so that is the end of this unit. That is Unit 1, Lecture 1. And I want to thank you all for staying with me and listening. For any concerns, please contact the numbers here below. Thank you very much. And I'll see you in the next lecture, which we will look at Unit 2. And that will be our second lecture. Thank you.